Hi everyone, this is Arezoo and I'm going to present on the behalf of our group on comparison of deep reinforcement learning and model predictive control for real-time depth optimization of a lifting surface controlled ocean current turbine. As we know, there is a growing need to harness power from ocean, and we have a high demand for novel methods of electricity production due to the increased interest in the renewable energy resources. Between different types of renewable energy resources, there is a high potential for power generation from ocean, such as 44 gigawatts from the Gulf Stream current and 5 gigawatts from the Florida current. So ocean currents possess large quantities of extractable energy and are very power dense in several areas. And today's focus is on ocean current turbine system as one of the novel types of renewable energy technologies. Okay, in this presentation, I first give you a background on our work and then the contribution of our studies. Then we see together the modeling of spatiotemporal uncertainties in the ocean current, and I show you the representation of our ocean current turbine system, which is designed for operation in the Gulf Stream. I just show you the formulation of our optimization problem to maximize the harnessed power from this system, which is solved through the model predictive control and deep reinforcement learning, and then show you the simulation results obtained through these two algorithms, and finally conclude our presentation and show you the future works to continue this work and related publications from our group. Okay, the ocean power density is depth dependent with the highest values near the sea surface. So it's very important to use some technologies such as lifting surface and buoyancy to navigate the ocean current turbine system through the water column and maximize the harness power from this system. There are a few literature to study this concept and maximize the harness power from the ocean current turbine system, which are very expensive technologies. So specifically, our contribution is to present quantitative comparison between deep reinforcement learning algorithm as a learning-based algorithm and model predictive control as a model-based one to solve the optimization problem for lifting surface control ocean current turbine depth optimization. Okay, first, we should model the ocean current. There are lots of spatiotemporal uncertainties in the current flow, which are resulted from turbulence, waves, lower frequency flow structures. And to model that, we use the real data. And this real data is recorded in the Gulf Stream. So we apply the Gaussian process modeling to predict the ocean current and model this environment. The ocean velocities are recorded in the Gulf Stream, and we have the Gaussian process modeling to model this data and then predict the future data. But we have some error, and we should consider them in our model. This error caused due to sensor error, simplifications in the spatial and temporal models, and imperfection in the ocean current prediction models. Okay, then we want to model our system. Our system is a lifting surface controlled ocean current turbine, which is optimally designed for operation in the Gulf Stream of the Florida's East Coast. This system includes twin rotors and a main wing and canard and wingtips, and which is attached to the ocean floor using the mooring cable. To model this system, we have 8 degrees of freedom, 6 degrees of freedom for the motion of the main body, and 2 degrees of freedom are considered for rotor's rotation about the x-axis. So after modeling the system, we want to obtain the power equation for lifting surface controlled ocean current turbine, and we just use the linear model. So the power equation includes two terms. The first term is related to the generated power from this system, and the second one is related to the consumed power to change depths. Okay, so we now want to formulate our optimization problem. We want to design a real-time spatiotemporal optimization for the lifting surface controlled ocean current turbine to maximize the harnessed power. In this regard, the ocean current turbine is treated as an autonomous underwater vehicle, but with the primary role of energy generation. So The main objective is maximizing the harness power from the system. To solve this optimization problem, we have two different methodologies. The first one is the model predictive control. For the model predictive control, we should at first define the cost function and then solve the cost function in the optimization problem due to operational constraints. But in the second approach, we just consider the learning-based one. So the ocean current turbine as an agent should learn the optimal policy from the environment and from its interactions with the environment. So we should define the reward, which should be specified based on the maximizing the harness power from this system. And then we should have a policy to harness the best actions and to choose between the best actions to find the optimal depths for our system. Okay. So for the first approach, which is model predictive control, we at first formulate our problem at each time a step to find the maximized harness power from the ocean current turbine, and we want to minimize the cost function in a prediction horizon to address our problem. So we should find a prediction horizon which is defined by an n sequence of optimal depths for our problem. And as you can see, we just formulate our problem with two different terms. The first term is related to the harnessed power from the system, and the second one is related to the standard deviation of the future estimated ocean current from the measured one. So we just want to solve our objective function due to the operational constraints. But for the second approach, which is the learning-based approach, we want to define our problem based on the Markov decision process. So we have the ocean current turbine system as an agent, which should observe the current state, takes the action to based on the learned policy, which results in the reward and state change. So we should define the states, the actions, reward based on the problem. Okay. In the reinforcement learning algorithm, our agent should learn how to map each state to the optimal action. And in our problem, which is maximizing the harness power, we define the state based on the current depths and the ocean current velocities. Then we have the actions, which are the depth change. And finally, we define the reward based on the increase in the harness power. And when we have an increase in the harness power, so we just specify a positive one as a reward to our system. Then we should define the policy for our system. We use the epsilon greedy policy to balance the exploration versus exploitation. At the first, we should have some exploration and just pick the random actions to see all the actions. And when we go through the final steps, we should only pick the best one. And the best actions are chosen based on the Q values, which is defined based on the Bellman's equation. Okay. Between different types of deep reinforcement learning algorithms, we pick DeepQ network, and DeepQ network is a neural network based reinforcement learning, which maps the relation between the states and actions. As I mentioned, we have some states, actions, reward, and we should find the best action between them. So the DeepQ network uses the neural network as a nonlinear estimation to find the optimal action estimation. And to find the weights for the neural network, we should solve the minimizing of the mean square error, which is defined in this relation. We have the target Q value, which is defined based on the Bellman's equation, and we should find the values of theta for defining our neural network. Okay, specifically in our problem, we train our DeepQ network based on the offline training using the recorded velocity, and then we use the optimal weights for the neural network and apply this in the real-time application. Okay, To test our problem and our proposed methodologies, we just consider two different cases. The first one is related to where we don't have any prediction error. So the deep reinforcement algorithm, to have some setting for this, we use only two hidden layers and then have some settings for this algorithm. And to train this algorithm, we use a 4-week measured ocean current data from August 20 to September 17, which are based on the real recorded data in the Gulf Stream. And then we test this system for a period of 1 week. We use the similar period for the MPC algorithm to compare the results obtained through this algorithm. As we can see in the figure, these algorithms are too similar in finding the optimal depths, and there are only a few changes in the optimal depths, and the average harness power from the MPC is equal to 692 and it's equal to 688 for deep reinforcement algorithm, which is almost the same. And it shows that both algorithms are suitable for finding the optimal depths in case of no prediction error. Meanwhile, the MPC algorithm follows the system and environment model, but the deep reinforcement algorithm learns the policy, the optimal policy from its interactions with the environment. Okay. The second case is related to where we have prediction error. As you can see from the figure, the optimal depths are too different from each other, which shows different policies for finding the optimal depths. The deep reinforcement algorithm is more error tolerant than the MPC one. The harness power from this system is equal to 644, which shows only 6% decrease compared to the baseline. But for MPC algorithm, we have 626 in the similar condition, which shows 9.5 decrease to the baseline. So the MPC is less error tolerant. And we should mention that the deep reinforcement learning algorithm can show better performance due to its capabilities to train in the offline mode and learn from the recorded velocities. So the results from the MPC can be improved if we improve the prediction, and the deep reinforcement learning algorithm can extract the robust and efficient high-level features from the noisy and uncertain ocean currents. So it's very suitable for our problem in case we have prediction error. Okay, finally, in this presentation, I show you a real-time spatiotemporal optimization for a case study of lifting surface-controlled ocean current turbine to maximize the harness power from this system. And we find the optimal depths for operation of our system. We just solved our optimization problem through two different approaches. The first one, which is a model-based one, model predictive control, and the second one, which is a learning-based one, and deep reinforcement learning. Okay, we just compare the results obtained through these two algorithms together for two cases where we don't have any prediction error and where we have prediction error. And we show that these two algorithms are both suitable for case we don't have any prediction error, but the reinforcement learning algorithm outperform the MPC in case of high prediction error. Okay, currently in our group, we just focusing on developing a nested coordinated control framework for path planning and path tracking. And you can see our representation from this in this figure. And we also are working on designing a coordinated control framework for an array of ocean current turbine, assuming wake effects between multiple ocean current turbines, optimal navigation, and collision avoidance. To continue this study as a future work, we are going to test the generalization issue for the deep reinforcement learning and justifying with a stochastic MPC. Also, we are going to investigate a robust MPC and robust deep reinforcement learning for rejection of disturbance and uncertainties of our model. You can see a list of related publications from our group in this slide, and I highly appreciate all your attention into our presentation.